Okay, I have discussed flash droughts elsewhere under extreme events, which is a series of podcasts I've posted. This nice paper came out which tries to differentiate the duration, intensity, and frequency of flash droughts and try to nail down what it is that is trending in the last few decades. So here is how they do it. Obviously, you are aware of droughts. There is the meteorological drought when there is just a rainfall deficit compared to the long-term average or climatology. There is the agricultural drought, which affects crops. Basically, soil moisture deficit should go down to something like root depth. So you have to be careful about what definition is being used. This particular paper is using the root depth soil moisture as definition. So here is an example as a schematic. Soil moisture in kilograms per meter squared, so it's storage in some depth of the soil integrated. So you have soil moisture itself here shown with these blue line, and you can see that it is trending down over these pentads, and then after some time it recovers. So depending on whether you use the drop as 50th percentile or 30th or 20th, you can get very different answers in terms of the intensity, duration, and frequency of flash drought. So you have to be careful. So here it is showing the 40th percentile, which is below the soil moisture when you start. So at this third pentad, it is soil moisture is here, beginning to drop rapidly, and within one pentad it goes just below 40th percentile, and then over these next few pentads it drops below the 20th percentile. So you can think of this as the onset of drying, and this is the onset point where the rapid fall in soil moisture begins to happen. Okay, so this is then the duration when you recover. So the definition is that it has to drop below the 20th percentile and then has to stay there at least something like 3 pentads. So here they are tracking the point where it goes back above the 20th percentile, and that's called the drought duration. And this is the onset of drying here, going from its full value to the 20th percentile. Okay, so if you used 40th percentile, you will end up with a different answer, and so on, and that's kind of the point. So here the period used is 2000 to 2020. When there is warming, of course there is always that global warming pause thing we have to deal with, but ignoring that for now, let's look at the comparison in soil moisture percentiles and the mean frequency of flash droughts according to different definitions from the perspective of intensification rate and duration. Okay, so these are the different data sets based on essentially models that assimilate data and produce some kind of a, let's say, reanalysis of soil moisture for the past period. So these are flash droughts, Gleam, NOAA, and the community land surface model, I think. Make sure you check to get the names right, but I want to focus on the points. So you can see that they have different soil moisture percentile drop rates here for these periods starting from T to T plus 1 pentad up to T.5 pentad, where the minimum has been reached and the soil moisture is on its way to recovery. And here is the heat wave flash drought or precipitation deficit flash drought, and you can see that for the same period the variation over time in terms of soil moisture percentiles are quite different. Okay, so we are looking at A and B, the temporal variations in soil moisture percentiles for flash drought events of all grid points shown here based on two definitions. Please note that soil moisture percentile represents the magnitude of the decline in soil moisture as shown in A, which was calculated for the whole time series, which is the study period of 2000 to 2020. C and D are frequencies of occurrence of flash droughts based on the two definitions. So here they are merging the heat wave flash drought, precipitation deficit flash drought, and doing the soil moisture percentile flash drought as the other definition. So you can see that the frequencies can be remarkably different. Here you're seeing here, okay, the color scales itself tells you how different the numbers you get from just changing the definition are. Okay, so intensification rate based definition, SM decreases from above the 40th percentile to below the 20th percentile with an average decline rate of no less than the 5th percentile for each pentad. So it has to drop by about 5 percentile points in each pentad, and the soil moisture below the 20th percentile should last for no less than 3 pentads. So once you hit the minimum, it has to stay there for at least 3 pentads. If the declining soil moisture rises up to the 20th percentile, flash drought will terminate. So if you drop below and then you come back to 20th, then the flash drought by definition is over. The duration based definition here, the pentad mean surface temperature anomaly is greater than 1 standard deviation. Evapotranspiration anomaly is greater than 0. Precipitation anomaly is obviously less than 0, and soil moisture percentile is less than 40% for heat wave flash droughts. The pentad mean surface T anomaly greater than 1 standard deviation, ET anomaly less than 0, soil moisture percentile less than 40%, and precipitation percentile less than 40% for the precipitation deficit flash droughts, and D is the total number of the HD, FD, and PD, FD droughts here. Okay, so these are kind of chosen as the high frequency soil moisture based flash droughts for further analysis in the paper, and I won't go into the definition, into the details here, but you can see various regions are shown for percentage of flash drought. The orange, I don't know, this is some yellowish color, is in the 40th percentile, and the greenish color here is so these are here the pentads: first pentad, second pentad, third, and out to 5th pentad. So the green one here is at 25th or so, and so on. Comparison of percentage of flash droughts at different onset times relative to all flash droughts and their temporal evolutions. So these are global proportions of flash droughts at different onset times relative to flash droughts. The red dashed lines at the top of the bar represent the range of uncertainty in the 3 data sets. So that's the standard deviation. Proportion of flash droughts at different onset times. So the B is here. So that's the A, and sorry, this is A and this is B. A is like a definition. Okay. B, proportion of flash droughts at different onset times relative to all droughts over 21 regions. So you can see the various scales here. C to E, temporal evolution of percentages of flash droughts with the onset times of 1, 2, 3, and 4 to 5 pentads relative to all flash droughts. The linear annual trends in the proportion of flash droughts at different onset times are estimated based on sense slope estimator, and statistical significance in trends are determined based on the MK test for the entire study period, which is 2000 to 2020. The shaded areas represent the range of uncertainty in the 3 different onsets. So the main point here is when you look at all the years and the percentage of flash droughts of all the total flash droughts, you will see that the one that grows in 1 pentad is the largest fraction, whereas those that grow in these other ranges of pentads are actually declining over this period, and that's also true for the C and E, temporal evolutions of percentages of flash droughts with onset times of 1, 2 to 3, and 4 to 5. So these two are dropping, which means the main message of the paper is that the trend in the flash droughts is mostly coming from the rapid rate of intensification of the flash drought, which is happening within 1 pentad. Okay, so it's not the intensity, it's not necessarily the duration, but it's the rapid drop in soil moisture percentile in the first pentad that is being dominated in this period of study. So in terms of drivers, interannual variations of flash drought affected land area and its related variables over the northeastern Europe and Mediterranean Europe from 2000 to 2020. So it's basically looking at land area anomaly in percentages, temperature anomalies in degrees centigrade, precipitation anomaly in millimeters per year, vapor pressure deficit in kilopascals, and soil moisture change in percentage. I think vapor pressure deficit is something you probably have already learned somewhere. It's what the atmospheric temperature corresponds to in terms of what the saturation vapor pressure is at that temperature and the actual vapor pressure that exists, which means when the stomata open, for example, if the vapor pressure deficit is high, it's going to lose a lot of water vapor, and similarly if soil moisture is facing a high vapor pressure deficit, is going to rapidly lose soil moisture. Okay, so here let's look at A to E, anomalies of flash drought affected land area and relative soil moisture changes over the northeastern Europe and Mediterranean Europe from 3 different data sets. Relative soil moisture change is defined as the change in soil moisture percentiles between adjacent pentads, current and the next pentad SM percentiles, where the positive values represent a decline in soil moisture at the current pentad. So that's what you have to keep in mind. B to D, anomalies of annual mean T, annual total precipitation and annual mean vapor pressure deficit over this region. So it gives you a sense of the mean that's there and the various data sets, and you can see that the data sets can differ seriously. So the land area here, you can see that sometimes they are in agreement, but sometimes they are not. So they are picking different time periods here, which are further shown in another figure. So you can see that there are times when the land area has increased significantly here in these boxes, corresponding to temperature anomalies positive here but negative here, positive in this whole band here. Precipitation anomalies negative on the other hand, and positive in this period, and negative here, and negative and positive here. So you can see the complexity of the role of temperature, precipitation, vapor pressure deficit on soil moisture anomaly in defining flash droughts. So one has to be very careful. So you can see that here vapor pressure deficit is dropping from the long-term average to maximum of minus 0.02 kilopascal, and then recovers here, then drops again and is positive in this whole region. Positive vapor pressure deficit is bad news, of course, especially with warm temperatures. Okay, so that corresponds to large percentage increases in areas with flash drought. Okay, so here is the corresponding soil moisture. Unfortunately not agreeing here at all, but there is a large negative here, and they are all somewhat disagreeing, but you can see again the soil moisture percentage change is positive, which means one pentad is drier compared to the next, and that's similarly here, large deficits in soil moisture in terms of percentiles. So the main story again is then you can define a relationship between soil moisture and vapor pressure deficit. So vapor pressure percentiles and soil moisture percentiles, and they are looking at these boxes which are chosen as the hotspots, which are in moist or humid regions and semi-humid regions, so not necessarily dry regions. So that's another thing you have to keep in mind. And this probability multiplication factor is basically saying when it's 1, there is no compound effect of soil moisture and vapor pressure deficit together, but when it's greater, then there is a compound event. So mean probability multiplication factor of concurrent extreme soil moisture, which is below 30th percentile, and vapor pressure deficit, which is above 90th percentile for the period of 2000 to 2020 based on 3 data sets. This is what this map is. In B, we are looking at the mean probability of percentile bins of soil moisture and VPD. So when vapor pressure deficit is small, soil moisture percentile is high, and you can see that if vapor pressure deficit is high, then soil moisture percentile will be low. So you basically move in this direction that they are highly correlated, and soil moisture deficit is going to be driven by vapor pressure deficit and vice versa. So it's a positive feedback there. C is the spatial relationship between the frequency of occurrence of all flash droughts and the probability multiplication factor of soil moisture and VPD extremes, again below 30th percentile soil moisture, above 90th percentile VPD. So you can see that pretty much a lot of events are amplified by the compound effect of soil moisture deficit and vapor pressure deficit. Spatial relationship between the frequency of occurrence of flash droughts and the probability multiplication factor of SM and VPD extremes. So here we are talking about the spatial relationship. So the soil moisture percentile is below 20th and vapor pressure is above 90th. Okay, so again you can see the frequencies and how they are affected by the joint effect of soil moisture and vapor pressure deficit. I wanted to include it just to tell you that we always have to look for duration, frequency, and intensity of these sorts of things. And the biggest trend in flash droughts over this period of 2000 to 2020 seems to be that the drop in soil moisture percentile, according to the definition chosen here, down to root depth, is that the number of flash droughts that are rapidly intensifying in the first pentad has increased significantly, whereas those that intensify in pentads 2 and 3 or 4 and 5 have decreased. So this is something to keep in mind, and I would say that's the main message of this podcast. Okay, if you want details you can read, but now flash droughts are taken as an extreme, hydrological extreme, as opposed to what we used to think of before as heat waves and extreme precipitation and floods. Okay.